All right, let's talk about C programming. We're diving into one of the most powerful parts, and yeah, sometimes one of the most intimidating. But here's the trick. To really get it, I want you to stop thinking about code for a minute. Instead, picture your computer's memory as this huge, sprawling neighborhood. And for the next few minutes, we're going to grab a map together and learn to navigate its streets like an absolute pro.
Okay, so this blueprint you're looking at, that is our map. I know, it might look a little complicated at first glance, but trust me, it shows how everything in a C program's memory is connected. We're talking everything from single tiny houses all the way up to entire city blocks. So let's take a guided tour, and we're going to break this whole thing down piece by piece.
So, here's the game plan for our little tour. First, we'll lay the foundation in our memory neighborhood. Then, we'll get our hands on this awesome GPS system. We call them pointers. After that, we're building whole communities with arrays and strings, learning the all-important street safety rules. And hey, by the end of this, you're going to be the one holding the master map. All right, Section 1. Welcome to Memory Neighborhood, laying the first foundation. Okay, so first things first. Before we can even think about navigating, we've got to see how the very first foundations get laid, you know? How do those initial houses even pop up on the block?
So check this out. Every single time you declare a variable in C, something as simple as int a equals 5, you're basically telling the computer, hey, build me a house. And what does it do? It immediately carves out a spot for this house in RAM and slaps a unique street address on it, just like the one you see here. And the crazy part? This all happens instantly, totally behind the scenes.
Okay, so what if you actually want to find out the address of one of your houses? Well, there's this little symbol for that, the ampersand. I kind of like to call it the where sign, because it's literally asking the computer, hey, where is this A variable located? And the program just spits back this super long hexadecimal address. And, well, that right there brings us to a huge problem. I mean, seriously? Who's going to remember an address like 0x7555F1A? And not just one, but hundreds of them. No way. It's totally impractical and just asking for mistakes. We need some kind of tool, right? A system that can store and use these addresses for us, so we don't have to. Section 2. Your GPS, mastering pointers, how to navigate the street. Well, guess what? That tool exists, and it's called a pointer. I want you to think of a pointer not as another house, but as your own personal GPS, designed for one thing and one thing only, navigating the streets of memory. Okay, this right here is the absolute key. When we create a pointer, with int times ptr a equals and a, we are not building another house. That's super important. What we're actually doing is creating a special little notebook, our GPS map. That and a part, that's us writing the address of house A directly onto our map. So now our pointer, ptr a, knows exactly where to find that house. We don't have to remember that crazy long address anymore. The pointer does all the heavy lifting for us. Now, here's where it gets really interesting, because there are two totally different things you can do. If you just use the pointer's name, ptra, that's like just looking at your map. All it tells you is the address. But if you put that little star in front of it, asterisk, ptra, we call that dereferencing. That's a whole different story. That's like using the map to actually go to the house, open the front door, and peek inside to see what's there. In this case, the number 5. So let's say you add 1 to your GPS. What do you think happens? In the real world, you might just move 1 foot, but in our memory neighborhood, adding 1 means something very specific. Move to the very next house on the block. And how far you actually move depends on how big the houses are on that street. For these int houses, which are 4 bytes wide, adding 1 actually jumps you 4 bytes over. But for those little char houses, it's just a single 1-byte step. Pretty cool, right? Okay, you gotta pay close attention to this next part, because it's subtle, but so important. It's all about prefix versus postfix. If you use prefix, so plus ptra, you move to the next house first, and then you peek inside. But with postfix, ptra++, it's the other way around. You look inside the house you're at now, and only then do you take a step to the next one. See the difference? The order of operations here literally changes everything about what your code does. All right, let's do a quick recap. A normal variable, that's the house itself. A pointer, that's your GPS map holding the address. Putting a star on that pointer, that's you opening the door and looking inside. And adding 1 to the pointer, that's just taking a walk to the very next house. Got it? This is the foundation for, well, everything else we're going to talk about. Section 3. Building with arrays and strings. From single houses to planned communities.
Okay, so we've got a handle on navigating between individual houses. That's great. Now let's zoom out a bit. It's time to stop thinking about single houses and start thinking about building entire, organized rows of them, what we in C call arrays and strings.
You know, at a high level, the difference is actually pretty simple. An array, think of it like a pre-built fixed row of townhouses. The address of the first house, that starting point, it never ever changes. A pointer, though, well, that's our mobile GPS we've been using. It's totally free to move around and point to any house it wants in the whole neighborhood.
And this visual here really nails the concept. See the array's name, R? It acts like a permanent street sign that's bolted to the very first house in the row. You just can't move it. But a pointer, it's completely independent. It can point to the first house, sure, but it could also point to the third house, or some random house all the way across town. So in short, arrays give you structure and pointers give you flexibility.
So, how do we actually work with these organized rows of houses? It's easy. We use indexes. These are just like the specific house numbers in the row. House 0, House 1, House 2, and so on. So if you want to store a grade of, say, 90 in that first house, you just write array of 0 equals 90. Boom, done. This kind of structure is absolutely perfect for any organized list of data. Think student grades, high scores, or daily temperatures.
Now strings are really just a special kind of array. That's all they are. It's a row of char houses, and each little house holds one letter of a word. But, and this is a big but, they have one absolutely critical non-negotiable rule. The row must end with a special house that contains a stop sign. We call this the null terminator, 0, and it's how you tell the computer, hey, stop reading, the word is over.
And that brings me to a super important warning. If you forget to save a spot for that stop sign, well, your program has no idea when to stop reading. It'll just keep on going, right past the end of your word and straight into your neighbor's memory. This is something called a buffer overflow, and it is just as bad as it sounds. It's literally like crashing a car right through their living room wall. This is a massive source of bugs and, even worse, major security holes.
Section 4. Street Safety Rules. Introducing the Neighborhood Watch. And speaking of crashing, that's actually the perfect segue into our next topic, because just like any real neighborhood, our memory map has its own rules of the road, and they're all designed to keep everyone and everything safe.
So here are the 4 big ones you've got to watch out for. First, pointer arithmetic errors. That's like miscounting your steps and walking into the wrong house. Then there's the null pointer. That's like trying to use a completely blank map. It points to absolutely nothing. A dangling pointer? That's even worse. That's a map pointing to a house that's already been demolished. And finally, a memory leak. That's when you build a bunch of houses and then just forget you own them, leaving them to rot and clutter up the neighborhood forever.
So how do we enforce all these rules? I mean, who's the neighborhood watch? Well, we call in the memory police, a fantastic tool called Valgrind. Think of it as an essential diagnostic program that runs alongside your code, acting like a street safety enforcer. It'll tell you exactly where you have memory leaks or where you're trying to use a bad pointer. It's there to save you from accidentally wrecking your own neighborhood.
Section 5. You now hold the map, the complete memory blueprint. Wow. Okay, we have covered a lot of ground. We've gone from single variables to pointers to arrays and all the safety rules. Now, it's time to put it all together. Let's look at the complete blueprint.
And there it is, the whole thing. This is the complete neighborhood of memory. And as you can see now, it's not just a random collection of separate topics, is it? Variables, arrays, strings, and the pointers that navigate between them, they're all interconnected pieces of one single controllable landscape. You're not just a tourist here anymore, you get the layout. You now hold the map.
Look, this knowledge, this is the real key to writing efficient, powerful, and truly safe C code. It gives you this direct, low-level control over the machine in a way that very few other languages even come close to.